This video is part 3 of chapter 11, describing data, confidence intervals, and correlation for PSY 222, research methods for the psychological sciences. In this part of the chapter, we're going to talk about correlation. Now, you've already got some practice through your Pallant homeworks and a description of what the correlation tests do. Now we need to draw back a little bit and get a firmer understanding of how we, from a design perspective, use correlation as a statistic. Correlation, as you know, are when you take two measures, two quantitative measures, and we test the degree to which they covary. And by covarying, we mean, do they tend to change in ways that are predictable? You're probably familiar from your introductory class, or if you took data analysis or the probability and statistics class in math, with images like the ones that I've found on Google Images and provided for you here. Like the idea that you can have strong positive correlations, strong negative correlations, somewhat more moderate negative correlations, more moderate positive correlations, or variables can have no relation to one another at all. When we do a correlational analysis, and again, you're familiar with this from your Pallant homework, we take the same steps that were outlined at the beginning of this chapter. First, you do your usual check for errors and outliers. Then you summarize the data. Now, there is the appropriate descriptive statistic, or not statistic, descriptive information for summarizing data for bivariate correlation. You could provide a scatter plot for that, and you know how to do that from your Pallant homework. Now, I rarely see, unless there's a very specific reason for it, I rarely see in journal articles correlations presented with an accompanying scatter plot. It's typically not seen as necessary. However, when you are doing your correlation analysis, it's a good idea to do a scatter plot just to visualize the data in your analysis. When you're looking at that scatter plot, it gives you kind of a chance to make some guesses just based on what you see in the scatter plot. Does it appear like I could pierce the scatter plot with a straight line and have that line be descriptive of the way the data points are distributed? And it can also give you a sense of whether the data should be moving in a positive direction or in a negative direction. The third stage is constructing a confidence interval for the correlation that you calculate. And remember that what you're doing with confidence intervals is saying to yourself, what's the chance that the statistic I calculate is actually going to reflect that population value, and setting up a range that would represent that estimate. The correlation coefficient, and you may have read about this the first time in, say, an introductory course, because usually we talk about correlation versus causation, and we talk about the idea of a correlation, even in those introductory psychology classes. Part of the reason is because a very large proportion of the research that psychologists conduct is correlational in nature and may in fact include readers having to interpret correlational data. Now, the correlation coefficient, and usually what researchers are going to use, is a Pearson product moment correlation, which is then represented with the lowercase letter r, can tell you a couple of different types of information. First is the magnitude. The range of possible correlations runs from negative 1.0 to positive 1.0, with the ones reflecting a perfect one-to-one relationship and 0 representing absolutely no relationship. between the variables. The correlation coefficient can also indicate for you the direction of the relationship. And the way I think about direction is this way. So I have two variables. They're both quantitative variables. Let's take an example from the data set you're working with for your semester project. If I have optimism and life satisfaction, and I've got scores. Every participant has an optimism score and a life satisfaction score. And I find a correlation of 0.48, and I'm totally making that up out of my head. I have no idea what the actual correlation is off the top of my head. But let's say it's 0.48. So it's positive 0.48. And that what that says to me is, as scores on optimism, the optimism scale, as those scores go up, scores on the life satisfaction scale also go up, and it's a moderate relationship, given the value of 0.48. Now, what about the relationship between optimism and perceived stress, however? As optimism scores go up, perceived stress scores tend to go down. And that's where the negative sign comes into play. It's also sometimes called an inverse relationship as opposed to a direct relationship. I tend not to prefer that language. I stick with the positive and negative labels just so that I can be clear about them. Now, this image comes from your text. If you ever need to remind yourself about how a scatter plot would look different in the case of a positive relationship, a zero relationship, or a negative relationship, you can use these visuals to help you remember. So if we replace X here with optimism and Y with life satisfaction, this would depict, if these were the actual scores, every little X there is a subject, is a participant, and their combination of scores graphed out. So each X on the scatter plot represents a person, and that person has two scores. So you're mapping out their combined location on the graph. If you have a zero relationship, that means there's no ability to predict. Scores on X do not predict scores on Y. They're kind of randomly placed. In a negative relationship, let's say you have optimism as variable X and perceived stress as variable Y. As optimism scores go up, perceived stress scores go down. And again, every X value is a person, is a subject, and it's their combined location of each of their separate scores on the two variables. Now, there are relationships between variables that are not straight lines. In other words, they're not linear. You can have variables where for a while it appears to be positive, then there's a negative slope, and then there's another positive slope. You can have what are called curvilinear relationships, where you have a period of time where you have scores that appear to have a positive drift, but then they go down. And this is, again, why it's useful for you, because both of these cases, there's something systematic going on, but the correlation coefficient, the R value, would be 0 because it's not linear. The R test is strictly for linear relationships. So running the scatter plot using your statistical program enables you to see that and say, oh, I can't really use a correlation coefficient like a Pearson test to test any hypotheses about the connection between these variables because the relationships are not linear. Now, here's another example from your text. Your author has given you two sets of scores. You have worry scores and concentration difficulty scores, and you're given in the descriptive information the means and the standard deviations for those two dependent variables. And then your authors have provided you with the scatter plot for the two variables. And just eyeballing that, what you can see is there appears to be a general positive trend. As worry increases, it's harder to concentrate. I'm sure that's a shocking finding for you. But it just is another example of how you can visualize the relationship between two variables with a scatter plot. Now, what you would report, and I've been, with our homeworks and with your worksheets for the semester project, I've been suggesting to you, anytime you have a quantitative variable, you're going to be expected to present means and standard deviations, and that's really what your authors are modeling for you here. Now, for those of you who dislike math, try to put your devastation at looking at these formulas aside for the moment. The Pearson product moment correlation, as I mentioned, is one of the more common statistics that we use in psychology, and what we're using it for is to test the association between quantitative variables. So in these formulas, X is variable 1, Y is variable 2. This big wonky looking E is a summation sign, meaning you add up something. N is the number of subjects in the sample. R is the correlation coefficient. So you know what the pieces parts are. When I first learned correlation, it was, I looked, this is called a definitional formula. Down here is a formula that's a version of it that is, I laugh, less likely for you to make calculation errors. And I'm like, yeah, right, I would probably make errors anyway. But if you look at this is the sum of X times Y. So you multiply your X with your Y. Then you have the sum of X, which is all your X scores, the sum of Y, all your Y scores. Down here, what you're doing is looking at some differences. So you're looking at the covariability, basically, the covariation of these two variables. As I said, the Pearson R is the most commonly used correlation coefficient. There are some non-parametric alternatives for it, and there are a variety of other kinds of statistics, but this is by far the most common. And as I said, X is referred to as the first variable in the relationship, Y is the second. The sum of X, Y, we call those cross products. So X times Y, you do that for each pair and you sum those. And as I said before, is the number of pairs of scores. When you're interpreting correlations, and before I go on, since we have statistics packages like SPSS, hand calculations aren't as necessary as they used to be. As you can see, these are very busy formulas, not the most crazy complicated formula you can imagine, definitely not. But you can see the tediousness of having to, let's say you had 400 subjects like we have, you would have to multiply 400 times just to get that component of your formula. So it's a good thing that we have statistics packages to do that for us. When we're interpreting correlations, you can make some predictions for each of the variables. And basically that means if I know the value of X based on the magnitude of the correlation and the direction, I should be able to predict the score for Y. If I had a perfect relationship between them, a 1 or a -1, I could do that with absolute clarity. With anything lower than 1, the magnitude of the relationship is going to determine how confidently you can make that interpretation. Regardless of the strength of the correlation, you cannot make causal statements. And the reasons are pretty straightforward. Think of optimism and life satisfaction. Both are complex psychological phenomenon. Your level of optimism is influenced by a whole host of things. Many, many variables affect optimism. Same for life satisfaction. Many, many variables go into how satisfied you are with your life at any given moment in time. If we find out that there is in fact a significant positive correlation between optimism and life satisfaction, you cannot say that optimism causes life satisfaction to increase, nor can you say life satisfaction makes people more optimistic. All you can say is that if you know somebody's score on optimism measure, you can, based on the correlation, you can predict that their life satisfaction will be higher. And if you know someone's life satisfaction score, you can also predict their basic level of optimism. But you can't say anything else. It's possible that the causal relationship goes in one direction, meaning optimism causes life satisfaction to change, or the reverse. Y could be driving X. Life satisfaction changes could affect optimism. But in a correlational design, we are not controlling for which came first, X or Y. Therefore, we cannot rule out, we can't determine which direction the variables, which direction in the direction in which they're causally connected. We also are not controlling for other variables that may impact both X and Y. So, for example, perceived stress. If and some of you ran into articles that you found for your semester project that were looking at mediator variables. There can be another variable that we could insert into this situation such that optimism is only related to life satisfaction if perceived stress is low at a given moment. Otherwise, then if perceived stress is high, you can still be optimistic while being highly stressed, and that may interfere with the relationship between those other variables. So what we're not controlling for is potential third variables, which produce what are called spurious relationships. Confidence intervals help you to determine, help you to estimate based on a correlation that you found for a sample, what the correlation value would be for a population, which is summarized with the Greek symbol rho. And that concludes this presentation. Now, you may be saying, well, why are you running us through a bunch of examples? Primarily because in your semester project and in your Pallant homework, you are going to be doing a bunch of correlations, at least a handful. And I've talked with you in my Pallant tutorial about doing correlations and interpreting them. So I don't feel like I need to waste your time talking about it more here in this context.